Today we're talking about geometric probability, and we'll start with the definition. Geometric probability is probability that involves geometric measures such as length, area, or volume. So in other words, probability in one dimension, two dimensions, or three dimensions. So let's start with probability with lengths. So the probability that a point falls on a certain portion of a segment is the ratio of the length of the favorable segment to the length of the entire segment. You may notice that this is just a restatement of our basic definition of probability, right? So it's the favorable chance over the total chance. So what's the probability that a point X is randomly placed between A and D and it's on the segment CD? Well, first we need to know the total length. So from A to D, if we count it up, the squares is 14 squares. So that's the total distance. And if you randomly place an X anywhere, what's the chance that it would be in this spot? Well, these are 5 squares. So there's a 5 out of 14 chance that it would fall in that spot. What's the chance of it falling on AC? So that would be this segment. So if we counted these up, that would be 9. So there's a 9 out of the total of 14 chance. And what's the chance that it's not on AB? So it'd be all the rest of this. So all of these added up are 11. So there's an 11 out of 14 chance that the X is not going to be on the segment AB. Point X is randomly placed on segment PT below. Find each probability. Now from P to T, because there's a number line, we can clearly see it's 0 to 40. And if X were to land randomly on P to R, what are the chances of that happening? So we know that the total number of possibilities is 40. And between P and R goes at, it's halfway between 20 and 24, so 22. So it'd be 22 out of 40. And we can simplify this to 11 twentieths. So it's an 11 out of 20 chance of landing on PR. What about the segment QS? That goes from 14 to 26. So out of 40, from 14 to 26, 26 minus 14 is 12. So 12 out of 40, which simplifies to 3/10. And finally, what is the chance that X is either on PQ or on ST? So PQ is 14. ST goes from 26 to 40, which is also 14. 14 plus 14 is 28. So there's a 28 out of 40 chance, which simplifies to 7 out of 10. And the other thing we could do is look at the fact that we calculated QS as 3 out of 10, and PQ to ST is everything else. So that would be 7 out of 10. This is the complement. 3 out of 10, 7 out of 10. Together they add up to 10 out of 10, which is 1. All right, let's look at a few of these applications down here. And they recommend that we draw line segments to help visualize the problem. So a radio station plays a commercial after every 16 minutes of music. If a listener randomly tunes in, what's the probability that at least 10 minutes of music are heard before a commercial plays? So let's draw a line segment. 0, 2, 4, 6, 8, 10, 12, 14, 16. So from the last commercial, they're going to play 16 minutes of music, and then there's the next commercial. What are the chances that if you randomly turn it on, you're going to hear at least 10 minutes of music before a commercial plays? Well, you would have to turn it on sometime during this 6-minute window, because after this, there's less than 10 minutes left before a commercial break. So there's a 6-minute window out of the total of 16 minutes when you could guarantee that that would happen, which simplifies to 3/8. So a slightly less than half chance that you would hear at least 10 minutes of music before a commercial. Okay, let's go ahead and flip over and take a look at probability with area. The probability that a point lands in a certain region contained within a larger region is the ratio of the area of the favored region to the area of the entire region. Again, this is just a restatement of basic probability that we've already learned about. So what's the probability that a randomly chosen point would land inside the shaded region in this shape? So first we would need to know the total area of the rectangle. And remember, that would be length times width. Length is 11. The width is 15 plus 8, which is 23. So 11 times 23 is a total area of 253 square feet. Now, our favorable area is inside this triangle, so we need to know the area of the triangle. Remember, the area of a triangle is 1/2 the base, which is 8, times the height, which is 11. 8 times 11 is 88, and half of that is 44. So 44 square feet. So our probability is 44 out of 253. And let's just calculate what our percentage would be. 44 divided by 253 is 0.17391. And then I would move the decimal 2 places to the right. So that would be about 17.39% chance. Okay, what about here? Here I've got a square, and then the corners are shaded with this circle cut out. So first I would need to know the area of the square, which would be 8 times 8, so 64 square miles. And then I would need to know the area of the circle. Remember, a circle is pi times the radius of the circle. The radius, so it's 8 across. The radius is half of that, so 4. So pi times the radius of the circle squared, which if we calculate it out comes out to approximately 50.27 square miles. But remember, this is not my favorite area. The part of the square that is not in the circle is the favorite area. So let's calculate that. The total area of the square minus the area of the circle is 13.73. So 13.73 out of 64. So if we divide by 64, that's 21.45%. Again, that's with me moving the decimal 2 places to the right. Okay, for this one, I would need the area of the triangle, which is, again, 1/2 the base, which is 50, times the height, which is from here to here. Now, this part is 12. I also know that this is 12, which is half the circle, and this is also half the circle, so this is 12 as well, so it's a total of 24. So 1/2 times 50 times 24 is 600 square feet. And then I also need the area of the semicircle. Remember, a semicircle is exactly half of a circle. So it'd be 1/2 pi times the radius, which I know is 12, squared. And when I run this, it comes out to approximately 226.19 square feet. So the favorite area is the area of the semicircle, which is 226.19 over the total area of this triangle, which is 600. So 226.19 divided by 600, moving the decimal 2 spaces over, that comes out at 37.7% when I round. Okay, one last section. Let's talk about probability with volume. A fish tank has the measurements given below. If the tank is filled with water to a point 2.5 inches from its top and a point is selected at random in the tank, what's the probability that the point is in the water? So volume of the tank, first of all, equals base times width times height. So all 3 of these numbers multiplied, which comes out to 3,456 square inches, no, cubic inches, because this is volume. And then the volume of the water in the tank is, again, the base times the width times the height, which is 2.5 inches lower than the height of the actual tank. So 16 minus 2.5, which is 13.5. So the volume of the water, if I multiply those together, is 2,916 cubic inches. So the probability that a randomly chosen point will be in the water, that's my favorable outcome, is 2,916 out of the total volume of 3,456. So 2,916 divided by 3,456. If I move the decimal over twice, that gets me 84.375%. So almost 85% chance. A sphere fits inside a cube so that it touches each side as shown below. If a point is chosen at random inside the cube, what's the probability that it lies outside the sphere? So this is just like my question with the circle and the square earlier, except that it's one extra dimension. So first of all, the cube has a volume of 14 times 14 times 14, which is 14 cubed, because it's a cube, so all the dimensions are the same, just like a square has all dimensions the same. 14 cubed is 2,744 cubic centimeters. And then the volume of the sphere, a sphere has a volume 4/3 times pi times the radius, which is 7, because it's half of the 14 cubed. And if I run those numbers, it's 1,436.76 cubic centimeters. So again, we want the area or the volume of the cube that lies outside the sphere, so we're going to subtract them. So 2,744 minus 1,436.76, that gives me a favorable area of 1,307.24 over the total volume of 2,744 cubic centimeters. And then if I figure out that percentage, divide by 2,744, and move the decimal 2 places over, I get 47.64%. So again, just a little under half. And that is geometric probability.